everyone. Welcome to the Fireside Chat. I'm Dilek Akkanitur from Amazon Alexa AI, and I do work mainly on conversational systems, natural language understanding, and language generation. And I'm with my colleagues, Alex and Bernard. Would you like to introduce yourselves? Alex?
I'm Alex Smola at AWS AI, VP and Distinguished Scientist there. My role is to design new algorithms that allow us to understand and analyze the data better on behalf of our customers and to build products and services. Before that, I was faculty at Carnegie Mellon University in the machine learning department.
And Bernard?
Hello, I'm Bernhard Schölkopf. I work for Amazon part-time for AWS, helping to start a lab in Tübingen in southern Germany on the campus or next to the campus of the Max Planck Institute there, which is where my main work is. I work as a director at that institute, and my scientific interests are in machine learning and causality.
Hey, thanks for the introduction. So it's amazing to be with two wonderful people on this fireside chat, especially since the topic is also conversational systems and language in general. So in the past decade, we have seen an enormous amount of advancements towards language vision, language in general. And we started seeing very large models becoming very popular. We want to start the conversation from there. Where do you think that we are going? What is the current status?
This is probably one of the most exciting things that have happened over the past decade, that we are now able to process and access a very, very large amount of text. And I mean, the one thing that probably seems like an afterthought is the fact that there's actually now accessibility of these amounts of text thanks to the internet. So basically the fact that people write content, that they put it up online, that you can crawl it, you can read and ingest and combine it, has drastically increased the amount of text that's actually available. So if you compare to what Project Gutenberg has, essentially, published books relative to what's now available, this change by many orders of magnitude has really allowed people to understand much better how people communicate and then to model this. Now, the quality of what you get obviously is varied, just like not everybody's a Shakespeare. I'm clearly not. But as such, you learn how actual humans to communicate. And you can then go and build good statistical models on massive amounts of text to understand or to begin to understand how dialogue works, how people interact, how they respond, and also to appreciate and learn some of the knowledge that's inherent in the text.
Yeah, so maybe I can add. So I remember when I was a PhD student, which is some time ago now, 25 years ago. I remember those days. I never worked on language at that time, or I still have done very little work in this direction. But I remember in those days there were still some people using like a first generation of neural networks. But by and large, the opinion was language, you use hidden Markov models, and neural networks are really going to be out of the business soon. And so this has changed by now, and it's kind of surprising. I mean, maybe in hindsight it's clear, but I still remember I was involved with this. So there's this deep learning project that was funded by CIFAR in Canada, which was started by Jeff Hinton first, and now it's run by Joshua Benjo and Yann LeCun. And so the first successes in this direction, when deep learning came back, obviously they were in computer vision, a particular kind of data, and many people felt maybe this is an area where neural networks make particular sense because you have this translational structure in images, you can use ConvNets, etc. And then at some point in this Canadian program, there was a discussion, so what's going to be the next big prize, the next big thing to go for? And I remember people like Joshua were saying, well, of course, it's going to be language that's ready for the taking. So, and I remember I was a little skeptical because I didn't know whether this system was generalized so well. But I mean, the empirical success stories are quite impressive. And I assume it would be interesting to hear from Dilek what she thinks is behind this. Is it the fact that we can now, that we have so much data that we can train much more complex models than just standard hidden Markov models? Or what makes neural networks special in processing language?
That's a very good question. I do think that it's a lot of data and ease of access to the data. Of course, the background models, they are also important as well. But I do see, like maybe by definition of my job, I do still see a lot of weaknesses, although we have a tremendous amount of progress. I do think that there are like still different problems that are remaining. Like maybe just to pick up on what Alex said, we do have tremendous amount of textual data. But when it comes to conversations, people do talk differently than they write. The distributions of the words change, the type of the things they say, the way they talk is different. So I think there is still some more way to go in order to have like fully naturally conversational systems. But I do remember the good old days of the Markov models. Things have improved significantly since then. I agree with that, but I think we are at a very exciting point in time. So, from your perspective, what are some of the things that are still remaining to be solved? What are some issues maybe not ignored but maybe less studied, and like, can we brainstorm on how can we solve some of these problems? Like, is data the only answer? Like, if we get more data, we will figure it out.
So it feels it's very impressive how, for instance, machine translation works now. It's very impressive how realistic the language is that we can generate. But if we think about those two tasks, it feels they're both tasks where if you basically have infinite training data, then even a relatively stupid system can do well. Essentially, I guess you could almost do well with some kind of lookup table system if you could just process your infinite data sufficiently fast. But as soon as you get to systems that, for instance, have a non-trivial state, internal state, and maybe that also have to have a model of the person that you're talking to, then I imagine it could get much more complicated, because then suddenly you have this combinatorial space in which you would need data, and I think that in real world we will never have that, even with internet scale data.
I think there's probably that the lion's share of the work that's still outstanding is to really disentangle between the how and the what. If you think about it, you can be very well versed in English and still have a very stupid conversation because the content of the things that you're saying just is pretty bad. Or you can be an amazing author, let's say in Japanese, and the translation of your book in English is amazing. And this is a very clear example of where content and the language are two separate pieces. And right now, what a lot of the success in language models has so far has only been is really to intimately tie those things. You could say, well, maybe, okay, I build a machine translation system and I combine this with an English generative model and we're okay. And even then you aren't quite, because the things that people write about in India are probably different from the things that they write about in Canada. And so polar bears and grizzlies and hockey are probably not things people in India care very much about, and cricket's probably more exciting. The more scary part is that if I just train a language model or on the content that I see, I have very little control over the, so to say, logical content. So, for instance, if I ask you the question, well, was Abraham Lincoln a vampire hunter? Everybody will be horrified and say, well, no, obviously not. Well, it turns out he is a vampire hunter, at least in some Hollywood movie. And the fact that you've never heard about it probably tells you as much as you need to know about that movie. But what you need to do is, therefore, is to have the ability to edit facts, to add content, and to also thus deal with essentially the type of content that you want to convey. And I think this, if anything, the past few years have shown us that it's very dangerous if you just repeat what other people say.
I mean,
I think this is going to keep us busy for the next few years.
It's interesting the way you put it. I mean, it reminds me a bit of when I think back how my kids learned to speak. So at some point there's this stage where they just imitate language. There's no sense coming out, but they try to imitate it more and more. And our kids, they grew up with multiple language in the house, and then for a while we had English as a secret language. They didn't understand it, but they were trying to imitate it at some point. And it feels like, and then at some point, as the brain grows, they also start making sense. So they leave this stage of just imitating. But the current machine learning systems, maybe they're still in this stage of imitating. There's just have a very huge toddler's brain, or probably pre-toddler's brain, that gets trained for a very long time, but doesn't progress beyond this intelligence.
I completely agree with that. That has been our experience as well, because the world is constantly changing. New things are happening, right? And if you keep looking back to the previous, whatever people were talking about before, how do you catch up with the new things? And oftentimes these things are local. Like it could be a cricket match in India. That is just happening right now. So how do you integrate the information to the conversation? Maybe it's a different formation translation, but in a conversational system, how do you integrate that information to the conversation in real time and then speak truthfully about it without hallucinating, because just mimicking a human would require does result in hallucination, which is, I think, very dangerous. So one of the areas that we closely look into is like, how do we get information from sensors? It could be structured. It could also be unstructured, like in new text that you can take from the web, from the news streams, and so on. But I think just being able to figure out when to hallucinate, when not to hallucinate, is quite tricky from the model's perspective.
So if we think about this phase that we're now in, so some people sort of talk about an AI revolution. And from my point of view, one could argue that this revolution has already started in the mid-20th century with the development of computers and symbolic AI and computer science and so on. But the big difference, if we compare that time and the current time, is in those days, the information had to be fed into computers in a highly structured way. So we had to present the information such that it's easy to process for computers, whereas now, using machine learning, we access information that's highly unstructured in the real world, and that's both in vision and in language. And then the whole difficulty and the reason why we need machine learning is that we want to be able to use this unstructured data. And I don't know, Alex, I think many of the machine learning problems are like this nowadays, right?
Mm-hmm.
Well, there's that, but I think there's a couple of other pieces underlying it. And as a matter of fact, we've seen a similar thing in physics. So once upon a time in physics, if you were good at spherical harmonics, you had a pretty good side gig designing antennas for GE and others. And this is basically how quite a few particle physicists made, their living, in addition to, discovering new particles. And what happened as computers became more prevalent, all this beautiful theory of spherical harmonics, which is gorgeous math that was developed at the end of the 19th century mostly, got swept away by just brute force simulations of, more general, less human accessible, less beautiful simulations, but that actually matched reality a lot better. So what happened is basically we've started throwing out the clean, concise formulations and approximating reality a lot better. What's happened over the past decade, probably in machine learning, is a similar thing where beautiful, simple linear models or hidden Markov models or, simple clustering approaches and so on have been replaced with a much more realistic view of, okay, well, this is what the world is. Let's use non-parametric tools to model the world as it is without necessarily imposing a specific structure. Right. And that's because we have a lot more data now, and also because we have many orders of magnitude more computation. So if you look at the amount of compute power increase over the past decade, it's gone up by about 3 to 4 orders of magnitude. If you look back 30 years ago, it went up by 1 order of magnitude.
Yeah, so I agree with you, and I think the tools that we use for this, I mean, you could say we now have tools to directly handle complexity in the world using data-driven mechanisms rather than spherical harmonics or whatever might fit well to a limited problem domain, and that's a dramatic progress. But nevertheless, in the end, coming back to a point from before, much of what we do is still pattern recognition and is limited to what people call the IID setting, so to the setting where you have independent and identically distributed data. So you have a data source which is constant, nothing changes, and then you get a lot of data from that source and you learn a model that predicts. So in a sense, what you're doing is you predict the future, but only subject to the condition that it looks the same as the past. So now if we want to get to more structured model, and maybe this is a slightly different notion of structure, but maybe related to what you said before, Dilek. If we want to get more structured models that maybe have a modular structure that explain where the statistical dependencies in data come from, without necessarily assuming that all dependencies will remain exactly the same, because in the real world mechanisms change all the time, and humans are quite good at transferring from one setting to the next one without being given a new 10 million data point training set to train on the new setting. So if we want to make progress in this direction, then we probably have to expand the current framework of statistical learning. And one such direction, I think the jury is still out how to do that, but one such direction would be to try to learn causal relationships underlying data. So I think that's a fascinating direction.
It's great that you brought that topic. So how can we apply the causal learning to language, natural language, in your opinion? What are some of the things that we should be looking at?
Yeah, I think that's a very difficult problem. So I've been thinking about this also quite a while already, and I haven't. I don't have a good answer to that yet. So one thing I was thinking about is about the direction of causality. So we had some work in the past where we are studying, suppose you have two quantities that you observe, and suppose one of them is the cause and the other one is the effect. And now you could have different machine learning problems. You could try to predict the cause from the effect or the effect from the cause. And for instance, in machine translation, it might be that your data set was generated by first recording a text in one language, and then a translator goes or comes and translates that explicitly into the other language. Then, in a sense, you have a certain direction of causation just from the way the data was generated. Now, from a theoretical point of view, if you have such asymmetries in data, in the data generating process, it has implications as to which machine learning methods make more sense or less sense, or which methods should work or not. And we've been thinking whether this could be applied in machine translation, but I think it's still an open problem, and I think we need more ideas, maybe also from the language area where people feel causality could be applied. And I guess causality would be, we have this so simple-minded view of causality, this mechanistic view it's related to something called structural equation models. But I think in language, probably people have a much broader view of what makes causality. You can even have causal statements in language, which adds yet another level of complexity.
So there's actually, this is quite funny. So a couple of years ago, we actually did analysis on multiple translations of a software package. This was back at Carnegie Mellon, and this was pre-deep learning. And we found out that it had a very strange dependency structure where German seemed to be at the root of all that language documentation. And one of my students, when we established this, I mean, he's now faculty in the UK, Seth Flaxman, told me, Alex, the results don't make any sense. Why is German the root of the software documentation? And it turned out that, yes, this was a small German startup that had been acquired by an American company. They translated it into English. They then moved some of the development team somewhere else and internationalized it. And then the documentation went to English, to Spanish and French and a few others. And so it was still visible, even though this was, very simple dependency analysis between purportedly, one-to-one translations between languages. So there's clearly signal there, as faint as it may be. But that's maybe not quite the causality that you were after. But basically, for instance, if I say something very stupid, you will be horrified. So there's a very clear cause and effect of Alex saying something stupid and Bernard and Dilek being horrified. Or if I say something funny, well, Dilek might smile, right? So by using these interactions, you can probably build interactive systems that will learn a lot better how humans will respond. The problem is you need to do this very responsibly because most people don't like to be experimented on. So it's, I think, a really difficult and fine line that we will need to walk there.
But it feels there are so many forces that are interacting in the background. Let's take just the language generation as an example. So many forces that's like that are influencing, causing what people utter, which some of which could be entangled in a way. So would it be possible to even disentangle them to figure out what is causing what and how basically the language generation?
Yeah. Oh, I think that's a fascinating question. Yeah. So so there's this field that people call disentanglement in the deep learning community or in representational learning, and I remember I had a lot of this even I think before this started. I think the current disentanglement wave was started with a paper by Joshua Benjo and co-authors, and I remember discussing with him in the years before that about, he was talking about that we, given some high dimensional data, we have to automatically learn the factors of variation. And I was trying to convince him at the time that I think that's actually a causal problem. That basically means we want to find a low dimensional causal model that gives rise to the high dimensional data. And I think in those days we were still quite far apart, but now these two things are kind of converging, and people are starting to connect causality and this field of disentanglement. And what makes it hard in this case is that, normally in causality, the assumption, in a certain way, the field of causality is mostly still at still at the symbolic stage. In symbolic AI, we were given the variables, and then we try to model relationships between variables. Whereas in machine learning, we work on raw sensor data or high-dimensional data, and the causality field is still, to some extent, in this symbolic stage that we assume we're given the variables. But maybe, maybe that makes sense, because even if you're given the variables, it's highly non-trivial to estimate what are the causal relationships between the variables. So there's sort of enough to study for a century there. But then there's this additional problem, which one could call causal representation learning, which is where, suppose you have high-dimensional data and nobody gives you the causal variables, and you have to learn both what are the variables, how to sort of extract them from the high-dimensional data, and then also how to factorize them and learn the relationships between them and disentangle them. And if you wanted to apply this to language, then clearly nobody is going to give you the variables directly. So you would have to learn it from data, and then I don't know if you interact with the speaker, then maybe there would be, I don't know, in an ideal world, you would maybe learn something about their intentions, their current frame of mind, what kind of information they're looking for, how would you best communicate it to them to be most helpful, and probably you can think of many other such factors, and that would be actually very interesting to think about.
So I agree. It's quite complex. So one of the issues that we mainly on the language, on the conversational side, have is like the ability to evaluate, to assess what is happening. Right. Oftentimes we do rely on human evaluation, kind of evaluation, which is not helping because humans are very subjective, and there's no perfect signal to even assess. Like if what you did is right, could there have been a better solution? That is, I think, hurting the field a little bit. So moving maybe towards evaluation, what do you think about evaluation in general? How do we, like, are we there yet? How do we assess when we are there?
So one interesting direction that we're seeing in some fields is now the emergence of what people call self-supervised learning, which it seems to be work quite well in visual tasks. So for instance, someone the other day was talking about an application where you try to learn how to track an object. You take a video and you just sort of start tracking in some place. And then you produce your training video to be analyzed by running the video forward for a while and then stopping it and running it backwards. And by this process, you know, whatever the object was, it has to end up in the same place again because you end up in the place where you started. So now you have a sort of an artificial video, half forward, half backward, for which you know if you have tracked the object for the whole time correctly, you better end up at the same place at the end. So it's a bit like, I guess, if you do machine translation, you translate from language A to B and then back from B to A. Should end up with something similar, but maybe there are more sophisticated ways of using this in language or even in conversations, like like a successful conversation. Maybe it has to converge to some kind of non-trivial endpoint. If you just end up in a loop, then it hasn't worked well, or I don't know.
So there are a couple of nice experiments that have been proposed where basically you build a bot that needs to convince people to do something. So for instance, donate $1 to a charity or, some other beneficial task. So this, and basically, they get like $2 to begin with, and they can keep all the $2 to themselves or donate it all to a charity. And you can then try to evaluate the bot based on how much able it is to convey and convince people to do something that seems more altruistic. So I think these are good test beds to make this work. The unfortunate thing is that pretty much all the things that work really well essentially work off patterned strategies. So for instance, I try to find out whether you're an empathetic person. And if you are, then I will use my empathetic pitch. And if you're a rational person, I will use a different pitch. And it's essentially almost like, okay, well, I put the other party into a drawer and then I use the playbook for that drawer. I don't think we've managed to really grasp the full diversity and richness of, essentially that's inherent in human nature and diversity. But I think that these are probably some of the earlier attempts now where you can actually quantify things, and that can be done in an ethical manner. Because this is really one of the big issues. I mean, you shouldn't experiment on humans just because you can. But the other thing is, I don't know whether necessarily causal directions are terribly static. So for instance, in a conversation, it may be that at some point somebody's driving the conversation, then somebody else takes over the initiative. And so it's it's a dynamic interaction. So you may be actually better off in some cases, for instance, using graphs and reasoning on graphs, and then basically using the fact that you have those relationships that are temporal, that are, and essentially building a statistical set of tools for reasoning on temporal and otherwise attributed graphs on it. And I think there's a lot of exciting work in this area. I don't think it's fully found its way into what to do with dialogues yet and into language. But this is probably, at least for me, one of the most exciting areas right now, where we'll see a lot of progress.
Yes, I agree. I think that's a fascinating area. And one other thing that somehow what you just mentioned reminded me of. So we at some point we worked on time series in Causality and trying to classify whether a time series sort of is forward or backwards. So if someone gives you a time series and may have reversed the time, and now the task is, can you classify whether it's forward or backwards? And I remember we had a hard time publishing this because the reviewers in the machine learning conference, they thought this is such a stupid task. Why would anyone want to know whether the time goes forward or backwards? But eventually it worked, and there are some asymmetries in time series. In natural time series, if it's the case that the generative process of the time series has a certain structure with independent noise added at every moment in time, etc. But if you take a time series such as speech or in language, or if you take a musical time series, then I think the issue of causality becomes much more complex. So you could imagine, I mean, I know, Alex, you're an accomplished piano player. In a piano piece, there certainly has to be some form of backward causation, because if a sort of a line goes towards a certain goal, then the causality maybe goes as much backward as forward, because it was composed in a certain way by a human. And I assume in language it's the same, especially in languages like German, where the verb comes after long elaborations. So you have this very much forward-backward recurrent structure, which you have to be able to process.
I mean, you might have this at different scales, right? So even in a musical piece, the overall flow of the piece, is linear going forward. You introduce a theme, and then you repeat it, and you vary on it, and you combine it, and you do all the beautiful things you can do. But yes, within a short scale, you will need things to be consistent. I mean, you already have things like the fact that you probably want to have matching gender. So for instance, if I introduce Dilek before mentioning her name, I will refer to her as opposed to him. And so it's not just in German and other weird languages like that, or in music, but you have that, I think, in pretty much any sequence generation process, that you need local consistencies that go as much backwards as forwards. But overall, at the larger scale, I mean, you would have to have linearity, because that's how humans ingest it. So that's, I think, pretty much human nature. But I should probably leave Dilek with the last word.
These are very interesting, actually, thinking backwards, because there are dependencies not just inside a sentence, but over the full discourse, or even like you may be talking about something and then showing some common sense reaction over after a period of time. I think it's interesting to think of backwards. But okay, I think we are running out of time, and it has been a real pleasure to talk with you. Thanks to both of you.
Thank you very much. It has been a pleasure.
Thanks a lot. And thanks for having the opportunity to speak here.